switch through the slides?
Sure. Tell me. I didn't bring glasses. Oh, I am.
And we're at
This is just, okay, it's just there. And
Yeah.
Is this the...
That doesn't do anything. Just forward and back on these.
Okay.
Hello. Good afternoon. Let's get started. If I can get your attention, please. Let's get started. How many of you are coming here for the first time? That's great. That's amazing. We have been trying to do this for years, and finally we know what the formula is, which is to hand the driving wheel to the chair of a department, and he brings everybody in. So thank you. How many of you are undergraduate students? Even better. That's also something we have been trying for some while, to bring more undergraduate students. I think we have succeeded on many counts. So thank you so much, Richard, and your team for helping us do this. Let me announce what we have going on next week. It's one of the special events we have every semester, just once a semester. It's called the Student Research Showcase, where we'll have 3 graduate students present their cutting-edge research on energy and environmental related issues. So please join us doing that, for that event. Today we have something that we have actually not done before. It's a very, very special event where we have several faculty from the Civil, Architectural, and Environmental Engineering Department who are going to present to us. And I'll not take much time. I'll invite the department chair and Professor Richard Corsi to introduce the panel and the panelists. Richard.
Thank you, Varun. Thanks. So as Varun said, I'm the chairman of the Department of Civil, Architectural, and Environmental Engineering. And for those of you that don't know, most recent national polls, number 3. Most recent international poll, number 6 in the world. So we're a good department. Yeah, I guess I have to do this, right? So I was asked to facilitate the discussion tonight, the panel discussion, and also to say a few words about the department and where sort of energy fits into our department before I introduce the panelists. But before I do, I want to thank the Energy Institute for giving us this platform tonight. I really, really, really appreciate it. All right, so what we're going to do tonight is I'll say a few words about the department, then I'll introduce the panelists. The panelists are each going to come up and do a 5-minute presentation, and I'm going to cut them off if they go over 5 minutes. And then at the very end, we're going to have all the panelists sitting up here, and you can ask the panelists all the questions you want as they're sitting up here. So that's the format for tonight's event. So a few things about our department. About 2 years ago, we did this deep introspective analysis of who we are, what types of thought leaders we wanted to be, where we wanted to go in the future. And we had a committee of 8 faculty members who spent an entire year thinking about that. So it wasn't a 2-week exercise. And at the end of that 1-year exercise, we came up with a whole list of recommendations in our strategic plan. And if anybody's interested in it, you can go to our website and just pull down under About, and you can read a lot more details about the plan. I'm not going to get into that tonight. But suffice it to say, the plan revolves around 3 major pillars. One is the rapid growth of cities, not just in Texas, but the nation and the world. The second is water, and you can appreciate in the western United States how important getting water of sufficient quality is for all of our needs as a society. And the third is energy, and that's the one we actually had the most discussion about. And it emerged because as we looked at our faculty and the kinds of research we were doing, we saw this sort of thread of energy research going on in our department that nobody ever really talks about. And so we see a future where we sort of grow that area, and we plan on growing these areas in terms of faculty hires. We've hired 2 faculty members. You're going to hear from one of them tonight. Since we developed this plan that it focused in energy or water or cities, and right now I'm negotiating with 3 more faculty members trying to get them here that all fit into this strategic vision. We're also making changes to our curriculum and developing some real partnerships around that strategic vision. So what do civil, architectural, and environmental engineers do with respect to the energy sector? One is energy infrastructure, and that's really big for civil engineering. If you look at an offshore oil rig, there's a lot of structural analysis that goes into the design of those things. If you look at how that's anchored to the ocean floor, there's a lot of geotechnical engineering design that goes into that. So we're sort of entrenched there in the infrastructure side. This is a nuclear power plant in Florida, a recent story about a nuclear power plant, whether it should be tabled or not. The decision was to try to keep it up and running for as many more years as possible. One of the things that has to be done to keep that plant up and running is to fix concrete cracks in the nuclear power plant. The estimate to do that is $1 billion for one plant. And we actually have faculty in our department who are focusing on fixing concrete cracks in nuclear power plants and getting a lot of money to do it. Another example, energy distribution, structural analysis of the systems we use to actually convey electricity, and then pipelines as well. So we're actually looking to hire somebody right now who specializes in non-destructive analysis of pipelines. And this is sort of local gas pipelines you see here in this image. Another is renewable energy. We have 2 faculty members working in the wind energy area. We have faculty in geotechnical engineering who are working in geothermal area, or at least trying to get in more research in geothermal energy. And then we've been having discussions about starting a new course in our department that focuses on wind and tidal energy, or wind and wave energy. So we have expertise in those areas, and we're thinking about advancing our curriculum in those areas. Energy conservation, transportation. Our transportation sources, I think, consume about 30% of all the energy in our nation, something on that order. So obviously that's an area that we need to go after, and we have a very large transportation engineering faculty, many of whom, and you'll hear from one tonight, do research in how we conserve gasoline. What can we do to basically make transportation systems better so we don't use as much fuel? Buildings, depending on which numbers you look at, anywhere from 39% to 42% of all the energy we use in our country we use in buildings. It's consumed in buildings. So if you take transportation and buildings together, that's 70% of all the energy we consume as a nation. That's civil and architectural engineering. Right? So we have a lot of research in that area. And about 75% of all electricity use in our country is used in buildings. I just have one slide here real quickly to show you Austin in the 1990s, about 4 years after I moved to Austin. This is looking up Congress Avenue towards the Capitol. You can see Austin in 1997 and the same view of Austin 15 years later in 2012, and you can see quite a significant difference. And that big significant difference, especially in the old warehouse district, is what civil, architectural, and environmental engineers do. It's buildings, it's roads, it's all the environmental stuff that goes along with that. And there are big energy implications as to how you design sections of cities. And lastly, energy and the environment. So we have a large environmental engineering program. It's also highly ranked internationally or nationally that deals with things like oil spills, coal slurry spills that contaminate the soil and other parts of the environment, and air pollution issues associated with energy development. So those are all examples of the kinds of things our faculty do in the fields of civil, architectural, and environmental engineering do. So that's just a little bit of background. I want to introduce the panelists now, and this is the order we're going to have the panelists come up and give their 5-minute presentations. But maybe I can have each of you stand up real quickly as I introduce you so that I don't have to introduce you when you come up here. How's that? All right. So our first speaker is going to be Lance Manuel. Lance is one of our wind people. Second speaker will be Charlie Werth. Charlie is going to talk to you about CO2 sequestration. Kevin Folliard is next in our infrastructure materials engineering group, who deals with concrete. Kockelman, who's our driverless car person in transportation engineering. She actually drives though, right? Yes, okay. And Atila Novoselac, who does a lot of research on building energy. So I'll now turn it over to them, and I'll have the timer on, and I'll come and yank you off stage if you pass 5 minutes.
Thank you. Thanks, Rich. Is this on? Can you all hear me? I hope so. So I tried to do this in 5 slides. It actually went through 7. So what I'm going to try to do is show how civil engineers have seen the energy picture emerge, and how some of the skills that we've attained through the years in different fields, mostly in my case, fluids and structures and uncertainty, informs design and practice for safer wind turbines. I'm just talking about wind energy here. And I'll include some work that graduate students of mine are doing on hurricanes, thunderstorm downbursts, which we know about in Texas, and they affect turbines and their safety or their performance, and then wakes, or the effect of one turbine on another and the performance deficiencies, if you will, that result from it. So for those of you who don't know, this is a picture from 1990. It's a very crude time lapse that you can actually get from a DOE website. In 1990, you can see a few wind turbines back in the West Coast, and the light blue is the number of wind plants that were built in that year. So in 1990, you see just one or two small little blue circles. Then you fast forward 10 years later, and you can see, when we go back there, we had 46 wind farms and 294,000 homes supported. We doubled that roughly in the next 10 years. But then the next picture is in 2012, which is a factor of 10 almost multiplied on what you saw before. And you'll see a lot of more light blue circles indicating the new projects that came online that year. So the growth of wind has been rapid. And recently, the Department of Energy, in fact, weeks ago, have put together a new scenario that they're envisaging about 20% penetration of wind to the total energy by 2030 and 35% by 2050. Now, these seem like ambitious numbers, but they actually exceeded previous predictions that they had made based on what we've actually seen with the wind energy industry. The picture here shows the orange pie chart portion shows how much wind turbines we had, wind energy we had through 2008, and the blue, which is almost as big in size, shows what we've got in the last 4 years. So it's clear that we've got a fairly brisk rate at which wind has made an impact on the total energy generation. This picture, this is the kind of problems some of my students are working on, which are the same things you would do for buildings or bridges and that kind of design. These are wind turbines in an array of 6 in Minnesota that all fell or somehow got damaged to different degrees during a downburst in Minnesota. And this is one of the pictures up close of that second turbine. And here we're modeling the flow field or the wind field. The wind turbine, the downburst that comes about from a thunderstorm is sort of like an impinging jet that sends out air in all directions and then creates some fairly large wind velocities in the red portion that you see. The blue star is meant to be a turbine, and the picture on the right shows the changing loads along the blades, shown by the reds being higher loads towards the middle and so on. And as the downburst moves towards the turbine, the effect is felt on the turbine, and turbines like this have fallen. The picture on the right shows an actual recorded, sort of a smoke, a dust cloud that creates that kind of vortex that you get, which creates, in turn, the complex wind field that we're designing for. This is the same wind downburst, and now the effect is felt on the entire array of wind turbines. And there's a lot of busy little numbers going on here. But there's an arrow that comes this way, which is the wind direction. There's a rectangle that's telling me what the loads are on the blades. And then there's a circle which tells me what the loads are on the tower of the machine. So as this is going through, you can see the wind velocities are changing direction and magnitude. And the individual turbines, when you see an arrow that's not perpendicular to the blade plane, that means there's an asymmetric load that the wind turbine that's trying to correct cannot do in time, and it puts severe loads on the machine. So that's kind of the idea that how we are dealing with complex flow fields during downbursts and their effects. Here's another example of things that we're designing for, and these are hurricanes. We've got no offshore wind energy yet in the US. We've got a lot of offshore wind energy in place in Europe, but the conditions in Europe are quite different from what we have here. We don't have hurricanes to deal with there. The waters are deeper because of the way the continental shelf drops off. And so on the picture on the right, you can see different points along the East Coast where planned wind energy development is in our sites, and how often, those are return periods, how often you can see category 5s and so on. And this picture on the top here shows what a typhoon did to turbines on land in Japan. So you can get pretty severe loads on machines due to hurricanes. And during a hurricane as distinct from a downburst, you actually know ahead of time that the hurricane's coming through. So you so-called park the turbine, or you don't let it operate. So these are simulations now of a parked turbine that's sort of in an idling mode. It's not trying to produce power, but you can see loads as this red circle moves through, which is the eye of the hurricane. As it moves through, it's creating loads on 2 turbines that we've simulated at these 2 points here. And the pictures on the top show how the wave heights and the wind speeds together are correlated and how they together have to be designed for when you're doing calculations. Finally, this looks like a Photoshop picture, but it's a real one. It shows you a turbine array where the front row of turbines creates large amounts of turbulence behind. It also extracts a lot of the wind speed or the wind velocities from the front, so that the second turbine is not only seeing less wind to create power from, but it also gets more turbulent flows, so it's going to be subjected to severe loading compared to the front row. So with a group at DOE, we're trying to do this modeling. This is a simulation of the same type of effect on the right there. And this shows how power production is compromised. If you normalize the power in, let's say, that red row, row 20, turbine 24 versus 29, you can see, or versus 30, you can see that the first turbine is producing a lot of power, but then in fractional quantities, you get about 40% in the back row, the furthest turbine. So those are some examples of the kind of things we've done. I know I'm out of time, so I'll stop there and I'll pass it on to Charlie.
All right. Hi, Charlie Werth. I'm interested in basically trying to sequester CO2 and doing that both in deep saline aquifers and also for enhanced oil and gas recovery as an alternative, more environmentally friendly fluid. So the challenge is climate models indicate that increasing CO2 levels are responsible for temperature and sea level rise. If you look at these plots, this just shows CO2. You've probably all seen figures like this where the CO2 levels are bouncing around, and then if you look in very recent times, you're getting this spike going up. If you look at temperature, you see over the past maybe 100 years, we've increased 1.5 degrees or so, and then you see the projections based on what happens with either business as normal or if we're able to prevent rising CO2 levels. And finally, this is sea level rise, and it just shows the rate of sea level rise and how it's increasing. And as I mentioned here, by 2100, sea level rise of almost 1 meter is predicted. So, some possible approaches to address that. One, we decrease energy consumption. Certainly there are some efforts there, but it's difficult with population growth. We could shift to lower CO2 producing fuels, and we're doing that with natural gas. There's a kind of a natural tendency for that because of the low prices and shale fracking. And it's already happening economically. But again, there's limited impact with population growth. We could replace fossil fuels with renewables. The work that Lance is doing in air power or wind power is fantastic. Oftentimes, these renewables have a low energy density. And so they can take a portion of our fuels or a portion of our energy right now. But all of it, at least right now, they can't. And so the last option, and there are others probably I haven't considered, but capture and store CO2. And in the Intergovernment Panel on Climate Change report, it's considered the lowest cost option to keep CO2 levels at 450 parts per million. And it requires 60% CO2 capture, and this would be from power plants by 2035. So it's a big challenge. The advantage to this approach is we're going to reduce atmospheric CO2. The disadvantage, and it depends on where you look at the cost, is that you're adding 20 to 30% to your electricity costs. And nobody wants to pay more for their electricity bill. The questions are, one, can we reduce the cost? So can we make it cheaper, or even more cheap? It's come down quite a bit in the last, let's say, 6 or 7 years. And then can we safely store this CO2? And so the idea is you could have an electricity plant or an ethanol plant or maybe a cement, steel, or a refinery plant. Whatever you're burning, you capture the CO2 from that. You compress it, and then you inject it deep underground. And you might inject it into a deep saline aquifer that might be 5,000 or 8,000 or 10,000 feet underneath the ground. You could also use it for enhanced oil recovery, injecting into a reservoir. You could use it as a fracking fluid, or you could go into a conventional reservoir and use it to displace oil. And that would also store it in the formation. So that's the general approach. In terms of the research that I'm interested in, we're looking at CO2 injection and trying to understand where CO2 is going and what reactions are occurring that are capturing it or storing it in the ground for very, very long time periods. So when you inject CO2 into the ground, you get this plume of supercritical CO2. It's a gas kind of liquid properties. It's expanding outward as you inject it. It's also rising because it's buoyant. And as it pushes out, it's displacing the brine or the fluid that's in the reservoir. As it does that, it's dissolving into the water where it's pushing out that water, and it's creating an acidified water because CO2, when it dissolves in water, has a lower pH. That's reacting with the reservoir materials, and that's changing them. And it can change the pore structure, so it can change how easy or hard it is to push that CO2 through the formation. It can also change how the formation is wetted. And so if you think about a sponge taking up water, if the sponge is wetted by water, you put the sponge in water and the water gets soaked up. If it doesn't, you put it in water and the water won't go up into the sponge. And so if you change those wetting properties, that also changes how the CO2 flows. The other thing that can happen is as the CO2 dissolves in the water, the CO2 can precipitate out as minerals, and so that can capture the CO2. And that's another way, when you inject it, to sequester or to store that over geologic time. So, a couple of projects we have. One is looking at how the wettability of these reservoir materials, or characterizing that reservoir wettability, and then looking at it, how it changes with reactions. And so a student, is Julian Boto here? No? Oh, all right, Julian, you missed your chance. All right. He's looking at this. He's basically taking, this is Mount Simon sandstone, where we have an injection project going on. And he's taking samples of this and looking at, this is a small cell where you have the sample, and then you look at how CO2, how the drops of that form, and how it's either wetting or not wetting on the surface of that sandstone. The other project we're looking at is trying to understand the processes that give rise to precipitation of minerals that are formed from CO2. So this is calcium carbonate, and carbonate comes from CO2. And you can see how it's clogging up the pores in this sandstone core. And here's just close-ups of individual pores in another experimental system where you see minerals forming. And then we do some fancy spectroscopy to look at what kind of minerals are created. And so basically trying to understand where the CO2 is going and how it's being stored. If we understand where it's going, we can understand if it's going to stay in the reservoir or if it's going to reach maybe an outcrop. We can understand how it's going to displace oil. And if we understand how it's stored, we can understand if it's going to be stored safely over geologic time. Thanks.
First of all, I want to thank the Energy Institute. My name is Kevin Folliard, and thanks for having us today. It's our pleasure. I'm in the concrete materials group or infrastructure materials group here in civil engineering, and I'm going to talk to you about some of the work that we're doing that's related to energy. Basically, I'm going to talk about three different areas that we're active in. The first one is basically using byproduct or waste materials, and these are predominantly from coal-burning power plants. And I'll speak a little bit about that and how this whole spectrum is changing and what we're doing to try to use as much of this byproduct material in an environmentally friendly way as possible. Then I'll talk a little bit more on the energy side in terms of hydroelectric power, and we've been active in looking at concrete dams that have suffered premature failure, and what can we do to extend the life of these dams, and what can we do when we rebuild the dams to get a serviceable life out of them. And lastly, talk about some new directions we're heading in terms of energy harvesting for civil applications. So I'll start first with fly ash. Fly ash is a byproduct from coal-burning power plants. In the United States, we still produce an awful lot of energy from coal-burning plants. And when you burn the coal, what you'll find here is that once you burn the coal, you'll be left over with a residue, which is a very fine powder. That powder can then be used directly in various applications. My area is strictly concrete. And the advantage here is we could use fly ash directly with no altering to that product at all. So we don't have to do any additional processing. And by doing so, we not only can be more sustainable, but we can also produce more durable concrete in the long run. So it's not just a matter of consuming waste, but it's actually producing better properties out of that concrete itself. Now our role in this is my only graphic here. I was so jealous of Lance's slides, I had to come up with something. We are essentially the trash man for the power plants. The way we use this is we have distributors who will pick up this ash, bring it to the concrete plant. We have absolutely no control over the nature, the chemistry, or the mineralogy of this ash. We're 100% at the mercy of the coal that's burnt, the way that it's burnt, and as we try to improve emissions, reduce emissions, NOx emissions, SOx emissions, and even looking at mercury, everything that's been done in the last 20 years to improve emissions has had a huge effect on the quality of the fly ash that's produced, and we can't do anything about that. All we can do is make the best of it, and in many cases, we will now have to do a little bit of processing or tweaking to the way we've used it in the past to still get good properties out of it. If you look at fly ash in our country, we produce about 70 million tons per year, plus or minus, of fly ash per year. About 2/3 of that is actually not used in construction, but rather it's put into landfills, either dry storage or into fly ash ponds. And what we're trying to do is find better ways to use the material and increase the amount that's actually used and therefore reduce the burden on these landfills. This is a dry landfill for fly ash. We've had 2 major failures of wet fly ash storage in the last 15 years, major environmental problems. And fly ash is a dangerous material. There is arsenic and all kinds of nasty material in there, but it's well known now that when you put that in concrete, it's essentially sequestered essentially permanently with very little leaching. So we're trying to not put it into these storage facilities, but rather put it into a lot of different concrete structures. One of the drivers for this is in fact the LEED Green Building Program, where in order to get certification for different levels, you are rewarded for using byproduct materials. In my realm of work, it's fly ash that goes into these buildings, and we've seen a huge increase in fly ash usage in buildings simply to get your LEED certification. However, with all the changes to the fly ash, we're finding it much more difficult to get these materials used without altering them, and that's where we're focusing on right now. The second topic I'll talk about very briefly here is looking at hydroelectric power. We still have quite a few concrete dams in the US and North America. Most of them have performed very well with very little distress. I don't work on any of those. I only work on the ones that look like this. Nobody ever calls me to look at good concrete. I've never got a call for that. This is the Mactaquac Dam in New Brunswick, known by the locals as Mactacrack Dam. It was supposed to last 100 years, and it has lasted 20 or 30, and it is slated for replacement in about 10 years due to a chemical attack which is occurring internally to this concrete, known as alkali silica reaction. Alkali silica reaction is an internal chemical reaction that occurs in concrete, and it occurs because concrete internally has a very high pH, close to 14. And at that very high pH, certain siliceous minerals will dissolve, and when they dissolve, they will actually form a silica gel, which is very similar to what you'll get when you buy a camera or any electronics. It has a huge propensity to absorb water. But inside concrete, when it absorbs water, it actually leads to expansion and cracking. We have 1,000 bridges in Texas that have ASR, and every state in the country has had this, except for Hawaii and Alaska. So it's a major cause of distress. And unfortunately for this dam, because the testing at the time wasn't adequate, it has failed very, very quickly, actually. And it costs about $6 million a year just to keep it in operation. It's actually grown vertically 7 inches, which I would say is good. You get more head, more water production, but the owners didn't think so. But But what also happens there is because the dam is restrained on the sides, when the expansion occurs, it ends up occurring more in the vertical direction. And the internal turbines now, instead of spinning in a very tight, round opening, they become ovaled. And the only way they can keep this in operation is by cutting slots in it every year with a diamond wire. They've taken out 18 inches across the length of that dam just to keep it in operation. This dam is going to be replaced in about 10 or 15 years, and I'm working with my colleagues at University of New Brunswick on the design of the new dam. And fly ash is, in fact, the answer to this. But we don't know if fly ash is going to be around 10 years from now. So we have to have other options, and in fact, we've gone into landfills and found that there is, in fact, enough fly ash in reserve below ground right now that could be used. So it's kind of a uniting of both the fly ash and the hydroelectric power. In my last minute here, just want to mention a couple new topics, and I'm kind of titling these Towards Energy Harvesting in Our Built Infrastructure, which means we haven't done anything yet on it, and we're looking for funding. This is an idea that we actually bid on a TxDOT proposal. Hopefully we'll get it in the future. The idea is to store water or de-icing or antifreeze below ground. If you go 20 or 30 feet below the ground, it's at about a constant 70-degree temperature. You keep that below ground. In the wintertime, when the bridge deck freezes, you have an automated kind of a smart bridge system that will predict precipitation. And then the heat from that bottom liquid is brought through the bridge deck, and the idea is to melt the ice before it actually forms. A lot of potential here, and we're hoping that we'll be able to move in that direction. My last slide is yet another direction we're hoping to head, and that is energy harvesting from pavements and bridge decks. This has already been done in other countries. It's being done in California. And the idea is that you would put piezoelectric materials, something like quartz, and these materials are unique in that when you apply a load to them, they actually generate electricity. That's the nature of piezoelectrics. The idea would be to harness that electricity, store it short-term on site, and use it just to light the perimeter of the freeway. So that's a snapshot of what we're doing on the material side, and thanks for your attention. Appreciate it.
Hi, everyone. I am a transportation engineer, so let's get this going. But I also have a master's in city and regional planning, so I don't just look at your travel choices, but also your location choices and your firms' and businesses' location choices and the built environment and how that affects transportation, energy, greenhouse gases, but also other emissions and crashes and traveler and community welfare more generally. So a lot of people, when they think about transportation, they think about congestion and their recent roadway experience. They often think about big infrastructure. And of course, there's a lot of operational and embodied energy consumed in these kinds of things. If you really get into energy, you start thinking about the size of your vehicle and its fuel economy, with biking being one of the most efficient, and of course the Ford Expedition being one of the least. Some of you are already owning, I hope, an electric vehicle or something that plugs in to try to take a hold of the renewables that Texas and other grids have as feedstock there. We've looked at entire years worth of data to get a sense of if you had a pure battery electric vehicle, how many days a year you would run out of juice if you only charged at night, so you only charged once a day. And it doesn't happen that often, fortunately. Those people can maybe borrow a neighbor's car or use car sharing or charge twice. We also looked at, in this picture, this is Seattle, and where the best locations would be for charging stations, so recognizing the total amount of parked vehicles you might have in an average day over, times duration, of course, and then walking distances to try to make that range anxiety come down for Americans who are very worried about being tethered. And of course, we don't have too many fast charging sites out there, so that concerns them with that particular fuel. And now many of you, I think, are thinking about the koala car. So I guess there's going to be about 100 of these in certain environments in this country before long, before the year is out, I think, is Google's plan. This has no steering wheel. And of course, it makes driving a little too easy. But it's cute and it's small, so it could go either way in terms of energy. So we've been spending a lot of time looking at that option as well. And just to give you a sense, with Google's Prius with the LiDAR device on top, and of course car sharing, and some of you are members, have been around for several years, so kind of putting those together. My current doctoral students adding the electricity, and so worrying about the range as a vehicle travels, as you can see on the right side, across the Austin network in this case, and picking up and dropping off. So it's a shared vehicle that can sort itself, which we can't do right now with the current shared bikes and shared cars out there. So that's a real problem for the operator of those fleets, is getting the bikes to where they're needed or the cars to where they're needed. But these vehicles can even anticipate neighborhoods of high demand and move themselves proactively before the call even comes in. And so we've also simulated ride sharing. So dynamic ride sharing don't have to have exactly the same origin and destination. And what we find is that over the course of days and years of these kinds of simulations, a shared vehicle can work about 10 times as hard as an individually owned vehicle, because our vehicles are parked 23 hours out of the day typically. So these vehicles stay busy for about 8 to 9 hours a day on average. They serve maybe 40 trips rather than 4 trips. They keep the wait times really low as long as you're not in a rural environment or a very exurban environment, so you don't have too many sparse locations. You've got enough calls coming in for the vehicles. And there's some empty travel, as many of you were probably estimating. And our simulations, it's going to be about 10%, hopefully less in more urban environments. And one nice feature is that the engine and the catalytic converters stay warm. And a lot of our emissions, I'm afraid, not so much our energy use, but other things that we really don't want to be spewing out, do come from those cold starts. And of course, once you electrify, then that disappears. The overall then, because we're using typically a smaller vehicle, maybe not as small as a smart car, but a Prius is a very fuel efficient vehicle compared to what most people are driving in this country. And so overall, you do get an energy savings. Is it enough to save the climate? Absolutely not. Okay. A lot more needed there. And one of the ways we do these simulations, this was an early simulation, so very generic setting. What we have is homes and businesses sort of scattered according to a normal sort of density profile for the region, and we just let the vehicles move from cell to cell based on calls coming in. And this is what that might look like if you were doing graduate research in this, you were starting out with this kind of topic. And so that's what it looks like over time, and the red arrows are when they relocate to better locations, hopefully anticipating demand. But we don't just look at the vehicles, remember, we do look at land use, and one of our recent forays is something that's in energy policy, a publication, is Austin. So this was our case study. We wanted to look very holistically at all of the infrastructure that's associated with transportation and housing and businesses and buildings and even lighting and water, things you can't see sometimes. And we took 5 very different neighborhoods, Westlake, Anderson Mill, Riverside, Hyde Park, and downtown. And we looked at kind of the shares of embodied versus operational energy, and especially in the less urban environments like a Westlake, there's a lot of money being spent on the pavement and the sidewalks, and a lot of embodied energy versus used energy. And of course, those pies really do get smaller as you move downtown. You reduce your energy consumption per year on average, taking the same person, not a typical Westlaker versus a typical downtown denizen, because they are different people, but taking an average set of demographics for Austin and moving them through the region, you can see this reduction. And more recent work is looking at entire cities where we try to mimic the city plan for Phoenix versus Orlando and New York City, and trying to get at all of that. So just very short examples of what we're up to. And if you're interested, there's a lot of papers here you can go to. And of course, we'll be taking questions in a moment. Thanks.
Hi, my name is Atila Novoselac. I have the fewest number of slides, only 3, which doesn't mean that I'm going to talk shortest. Anyway, I'm going to talk about buildings, and Rich already introduced some facts about the buildings. So buildings are the largest consumer of energy, approximately 40% of total energy, and also when considering only electric, 74%. There is one extra information which I need to add to this, is that most of this energy is consumed in buildings for environmental control, heating, ventilating, and air conditioning. And pretty much improving building in this field will produce significant results. So also very strong motivations for considering building and energy is the peak power demand, electric peak power demand. And here on this pretty much slide, you can see ERCOT energy consumption for a typical day in the summer. And you can see that pretty much during the night and during the day, we have increase of almost 100%. And this one here pretty much already hits the limit of our electric grid, which means that, and I need to add practically that this spike in afternoon hours is caused by buildings, residential and commercial, but mostly residential buildings and air conditioning in residential buildings. Interestingly, pretty much we have now significant change in building industry, which is not motivated so much with some kind of energy saving, energy in kilowatt hours, but more by the fear that we're going to run out of throughput through our grid. And we have now significant improvement in the buildings caused by this peak demand, limitation to peak demand. And one of the problems which we are working is definitely this, but we also improve energy efficiency by building envelopes, HVAC systems. We are developing strategies for retrofitting buildings to address this problem about demand response. Demand response is practically shifting actually these loads from peak powers to off-peak period. And also buildings are very crucial for any kind of renewable integration. So especially residential buildings are the largest source of photovoltaics integration with the buildings. Of course, users are the most important, and education is one of the problems which we are working on. I'm going to talk about two examples, present two examples how we work with building problems. And one is about chilled water storage systems or thermal batteries, pretty much. What you see here is UT Austin chilled water storage tank, which we built a few years ago. And the purpose here was to replace one cooling tower. Instead of building a new cooling tower, we decided to build this thermal storage system, which is charged overnight when our cooling systems have a lot of capacity. And then instead of adding one extra gigantic chilling station on campus, we can actually glide on this extra chilled water energy during the peak hours. And pretty much that saves some money, but also it can improve efficiency of the systems. So these thermal batteries are crucial for integration of photovoltaic and wind systems, so renewable energy systems into our buildings and the overall grid. Because most of the time we don't need all the electricity which is produced by wind farms. And one way how we can store this energy is batteries, electric batteries, but they are so expensive for large electric storage systems. And one way how we do that is pretty much we could use this electric energy to produce chilled water, store it, and use it when we need it. Pretty much it cycles on a daily basis. Also, other application for these thermal batteries are triggered by large addition of distributed generation systems. Again, to resolve some problems related to the grid, outdated grid infrastructure, we are pretty much adding a lot of these power distribution systems, again, which we can improve actually using desorption chillers and storing pretty much this thermal energy in the tanks. So you can see these thermal tanks are the not nicest picture, and one of the problems is that they're gigantic. So what we're doing, we're making them compact. Specifically, Steve Bourne, a student, PhD student, is working on the problems, on solving these problems using phase change materials. Practically, you can have size reduction from 10 to 15 times, but that's theoretical. The major challenge is at which speed are you going to be able to pull out. And the problem which we are working is optimization when we look at dynamics and density of thermal storage systems. You can see pretty much some prototypes. The first one, there was a lot of modeling prototypes. Second, and now it's integrated in pretty much School of Architecture. You can see it is operating. In this summer, we're starting pretty much operation when we're looking at these optimization algorithms for application of these thermal storage systems. The second example is showing how we deal with residential systems. Residential systems consume actually 50% of that, as much as commercial buildings. And the problem with residential buildings are that we have very limited resources. We have to find a solution which is cheap so that you can still afford your houses. And even though I have been working mostly with high-end technology, actually this was quite challenging problems which we tackled, looking how to solve the problems without any extra resources. And one of the problems is which we're looking is to identify fault. Pretty much every second or third house in US has some level of fault, and specifically for HVAC systems, either you have condenser fouling, or you have low refrigerant, or you have duct leakage, and these are gigantic sources of inefficiency which can consume 50% of your HVAC bill. So the problems which we are using, the solution which we are trying to incorporate is pretty much using a technology which is already present in buildings. That's smart meter technology. And a PhD student, Kristin Cetin, she's working on fault detection using just smart meter data. So smart meters are collecting data about total energy consumption with a high frequency, and now using disaggregation methods we can identify exactly a signal which is coming from our compressor or fan, and practically analyzing these signals. You can see this red line is a signal from the compressor, and using some normalization and algorithms for fault recognitions, we pretty much developed methods when the utility companies can identify inefficiency and send you with a bill check engine light. So this is practically a method how to identify potential problem in your building. So these are two problems. We have much more which we're working on, but here I'm going to stop with this one.
Okay, so if we have a few minutes or 10 minutes or so for
Yeah, right here.
We have about 15 minutes for questions. You can ask anything you want.
You're in a good place.
I hope
No, you're okay.
you heard pretty significant diversity of research in our department that all come back to energy, either at the fringes or direction. We have a lot of work going on. We have about 10 other faculty doing work in energy in our department, and we're hoping in the future, next academic year, we can have more events like this to showcase what they're doing. But lots of cool stuff, and I actually have more information now about what the faculty of our department are doing, so I appreciate it very much. Questions?
Yeah, so the way this works is I'm going to go around. We encourage students to ask the questions. And also, there's a sheet up here on the rail in the back. If you want us to send you the notification for our weekly flyer about who's going to speak the next week, please just write your name and email there. So, questions?
Hi, my question is for the building, especially the thermal battery. So, do you see a lot of progress in thermal battery at the residential scale? I recently saw a boiler that has a main tank and a storage tank that the grid operators, the electricity suppliers can control and heat when the electricity rate is low. So, like, what are your thoughts on that?
Turn on the microphone. Can you hear me? Yeah. So, yeah, definitely. One of the prototype which you saw, actually, that's a residential scale. And on a residential scale, they can be used. The one current limitations is the cost. Still, that prototype there cost $15,000. We hope that we can cut it down to $1,500 so that it can be affordable to. But definitely, it's quite large opportunity to move these thermal batteries to residential buildings, pretty much. And I think that's the major motivation of my students. So he can answer a bit more about it.
Do we have a question over here? Will you pass this to him, please?
Hi, yeah, my question is for Dr. Folliard regarding the fly ash. I was wondering if there are any kind of general trends that correspond to the quality or the type of coal that's being burned, whether like brown coal produces either more per metric ton or has more impurities.
First of all, very, very good question. Yes, there's a major trend right now with fly ash, and that is that people are switching to a very particular coal from Wyoming known as the Powder River Basin. That coal actually burns a lot cleaner. It's especially good at reducing the SOx emissions. It completely changes the chemistry and mineralogy of the fly ash. It also produces one-third fly ash, one-third the volume of fly ash compared to the eastern type ashes. In fact, there have been power plants in Texas, some of the biggest ones in the last 5 years, have switched coal sources overnight. And the chemistry of that ash changed so much that it turned into a different classification of fly ash, and it's no longer allowed to be used by the highway department here. It doesn't meet their specification. And in fact, if you're in an environment where you have a lot of sulfates in the soil, you'll actually make the concrete much less durable than concrete without that fly ash. And that is a major, major crisis for the state of Texas. We've lost probably 30 or 40% of our good Class F fly ash, which is a lower calcium ash. And secondly, people are now also using natural gas instead of coal, which is, of course, much cleaner, but it produces no ash. So the quality is... so, good question, thanks.
Howdy, my name is Kevin Merrill. I'm a master's student at the OBJ School for Public Policy. Real interesting talk. The question I have has to do with the common theme in this energy discussion, that current CO2 projection models on the impact for climate change are all projecting as if we were to maintain the status quo as a continual increase. However, as you just demonstrated, we are studying these problems of inefficiencies and incorporating them into new methods. Yet that is not reaching the public discussion. Instead, it's more of a we have to do a much greater, emphasis on changing everything. So my question, I guess, is implementing simple efficiencies and replacing older infrastructure, what impact does that have over the billions or trillions of dollars that we would have to spend to completely redo the entire...
I'll pass that.
Well, yeah, I was asked to go to D.C. to serve on a National Research Council committee about how land use decisions affect energy, and I kept saying to my group, I think we need to look more holistically because there's a lot lower hanging fruit out there, and the lowest hanging fruit is closing those docks and adding that refrigerant and insulating your home and getting your parents and your friends' parents to put, solar panels now on the roof. Things like that are really things that we can and should be doing, and people are not. But I think renewables, moving to renewables in the feedstock is really important on the power grid too. That was one of the lower hanging fruits, Changing built environments is really not. That's a very long-term, expensive, difficult process versus people's willingness to pay for living in different settings. So in terms of transportation, it was very hard until you went into multifamily, high-density downtown to get people's vehicle ownership down and their miles traveled down enough to really see a big impact. But of course, the infrastructure is much more efficient when you get into those dense settings too. It's not just the travel distances and the vehicles chosen. There's a lot to be done there. I did want to pick up on that SO2 comment that you made with the Wyoming coal source. I think it's the whole western half of the U.S. that gets almost 100% of its coal now from clean coal, but it's not as clean as I had wanted. One of the studies we did recently was about electricity and emissions costs for human health per mile traveled in a conventional vehicle versus an electric. And the SO2 that's still formed there, as clean as we think our plants are, they are not clean. And as clean as we think that coal is, it is not clean. And it is being carried downwind hundreds of miles and forming a very fine particulate that's lodging deep in the lungs and is reducing lifespans and really causing early deaths far more than you would have anticipated. We were very surprised to find that we still need to do a lot better on our grid sources of energy. Does anybody want to continue that complex question?
Maybe just a short comment. I think the projections I had up there were from the Intergovernment Panel on Climate Change. I think they're a few years outdated now. I think there was some anticipation of changes in efficiencies and changes in infrastructure and shifting to renewables, but I think as of, 3 or 4 years ago, at least, it was anticipated that those changes wouldn't be near enough. And so in the next 20 years at least, I think at least the conclusion of the panel was that you had to sequester that CO2 somehow coming off of conventional power plants. Now, I don't know if they went back and did that today, if it would be updated, and I haven't seen any recent literature on that. I haven't looked for it, so that I'm not sure about.
So I've got a wind turbine question. So as we go from, say, 2 to 3 megawatt turbines up to 5 megawatt, just to harvest better, get better capacity factor and such not, are the new techniques, new construction techniques, new materials used to upsize those, do they make them inherently a little bit less susceptible to the downdrafts and the hurricanes and such not, or just that size to harvest and get better capacity factor? Are they more susceptible to the phenomenon you're studying?
So the larger turbine, the larger rated turbines like 5 megawatts and 6 megawatts and all, are typically being anticipated for use offshore. So the offshore environment to begin with is different. Turbulence is less because you've got a nice smooth ocean surface instead of terrain features that we have on land. So that kind of reduces the impact when there are no storms. But now the hurricanes are things that we don't even know currently if we're going to design for them or we're going to just replace blades. So the answer is we don't know what we're going to do. The design philosophy is not yet determined for the U.S. The regulatory environment for the U.S. is quite different from what it is in Europe. Europe, 5 megawatt machines, which are not yet mainstream, they're not being used everywhere, have not seen as much damage. There's shallower waters, there's no tropical storms and so forth. The turbine itself is going to sample a larger swept area, and so in principle the variability across the rotor is going to be greater. From that point of view, the uncertainties related to loads over the long term, 20-year service life, will be higher. But most of these turbines have not had lifetimes that have exceeded about 10 years. We don't have enough of an experience base. More often than not, we're replacing things that you don't hear about because the developer and the manufacturer have come to an agreement that there's enough maintenance being done, especially in an ocean environment, to maintain the cleanness, the cleanliness, if you will, of the blades and so on. But the local sort of roughness features and all on the blade have compromised blades to the point where larger turbines have needed more action in terms of maintenance. As far as failures, we don't know too much, and that data is really not shared. Okay.
We have time for one more.
Hello, just real quick, I was wondering, do we have any CO2 sequestering in place now, or is it all in developmental stage?
There are several demonstration projects in the U.S. I've been involved with one in Decatur, Illinois, and they've injected a million tons of CO2, and they're planning to inject another million tons over the next year. That's still a small amount compared to what you'd need. I think is probably a couple of, factor of 100, let's say, smaller than the capacity you need for a power plant. If you look, there are a couple of very large injection projects overseas. There's one in northern Africa where they've injected very, very large amounts of CO2 without escape. In that case, it's interesting, you've seen the ground surface rise a few millimeters because of the increased gas storage underground. And then there's one in the North Sea where they've injected a lot of CO2, and that's for enhanced oil recovery, but it's very, very large volumes. So they have injected it without any detection of CO2 escaping in very large volumes. And then in the demonstration projects in the U.S., there haven't been any escape of CO2. Of course, we're talking about time scales here that are on the order of years or tens of years and not geologic time scales, but yeah. Thank you. Mm-hmm.
We can do one more.
Hi, I had a question about the load cell that could generate electricity. Could you use those in situ to charge the electric cars? Like, could it sit there and charge, or would you have to drive over it?
Yeah, I don't think you drive over it now, but I have to admit I'm not an expert on the technology itself. We were just trying to get it into pavements to generate the electricity. I think the bigger issue is the economic viability of this. They've done some case studies where they looked at putting it in, say, a mile of pavement, and the price was extremely high. And I think if you look at the recovery in terms of getting your money back on it, it's not even in our lifetime. And that's the real challenge, is making these piezoelectrics much more efficient. And people are looking at now stacking technologies where you can get as many as possible in one area, directly under the wheel path in the truck lane. But as to the ability to charge, I'm going to let Car answer that one. She's the car.
Yeah, it is a pavement question too, and I always tell people I just do not see how that could ever compete with pulling off the road and doing a fast charge, which is not easy on the battery and it's not cheap, but boy, compared to hoping that your pavement can also serve the purpose of charging en route with a remote, it's not wise in my understanding, but maybe there'll be some special surface coats that we'll use eventually that'll be inexpensive and can handle the loads on that pavement.
Thank you.